Hey everybody, welcome back. Today we're going to be looking at two different statistical tests. One is called the ANOVA and the other one is called the chi-square test. So this is going to be a series of two different shorter videos. So far we've been looking at the t-test. We've been using to compare two groups. They could be paired, they could be unpaired. And we're making a hypothesis about the two population means that supposedly produce the data. The ANOVA, you can think of it as something that generalizes the t-test. So you can compare three or more groups using their averages. And you're then concerned about the population means of as many as capital G total number of groups. And our null hypothesis, right? If we had a t-test, a null hypothesis would just be this. But with an ANOVA, our null hypothesis is actually quite strong, and that is that all of our G means, all of our group means are identical. And the alternative, let's write that down. All population means are identical. The alternative is at least one is different. And of course, there's a mathematical expression for this, but it's just not worth writing out using a bunch of different notation. Recognize this is a very strong null hypothesis. If you thought that equating two population means together with a strong null hypothesis, then you're equating all of your population means together. And you're saying the null is that there is no difference at all between any of the population means. Your alternative is at least one of them is different. But unfortunately, as we will see, the ANOVA is not going to tell you which one. So something to think about with the ANOVA, you will run into it. It will be reported in clinical journals. It is what is called an omnibus test. Write that down. It's called an omnibus test. It tests for any differences at all between your population group means. It's not going to tell you which one is different. And so if you're sitting there and asking, well, boy, what use is that? Sometimes it's useful to say that, where you have a strong expectation of homogeneity in the means, then saying that at least one is different is informative. Remember, all of this hypothesis testing is only informative if your null hypothesis is informative. So if you're applying this to the case where this is silly to expect, maybe the ANOVA is not a great place to start. If you're applying this to the case where maybe it would be meaningful to either fail to reject, like look at all of these different groups and there's no significant difference at all between any of the population group means. If that's a meaningful scenario to you, the ANOVA is your friend. Okay? So this is going to be a little bit hand-wavy because I do not want to focus on the ANOVA. I think it has limited usability and usefulness. But there are a few examples where it is a useful test. So here's my null, here's my alternative. Your data would look something like this. You have some response variable, some quantitative, usually continuous response variable. Here are your three groups. We have three groups, so we no longer can use a t-test. It's a test for differences. And I'm just using a dot plot here. So you have 5. So we have n equals 5 per group. Okay. 5 in each group. I've marked where my sample means are. And in that example, it would probably be pretty easy to determine that my group, population means are different because, well, the way I drew it, there's very little overlap between the data within each group. But you can imagine, suppose I increase this, I don't know, 10. and I start, overplotting more data, and I start overplotting more data, I now may have figured out that, well, maybe these two group means are no longer significantly different, but maybe all of them are still different from C. So this is gonna might reject the null hypothesis because our null is that all of the population group means are the same. So as with the test, with the t-test, there is a test statistic. The test statistic is the F. And it's called the F test statistic. Sometimes, though quite rarely, this is called the F test. And you may have guessed that the sampling distribution will be the F. Sampling distribution is the F distribution. Okay, what parameters does the F distribution have? Well, remember the t-test, the t distribution has the degrees of freedom. The F distribution has 2 degrees of freedom. And for now, we'll just mark this as df1 and df2. And we're going to just pause that bit for now. I will explain what these degrees of freedom are in just a second. Okay, so the first thing I want to do is kind of focus on our intuition about how this F statistic is computed. Remember, as any test statistic, it is computed only using your observed data. So this ANOVA is a ratio. It's a ratio. And it's going to be a ratio of between group variance divided by within group variance. All right. So we haven't dealt much with the variance, but I will just make a note. Right, the variance is the standard deviation squared, and it's tied to the average distance. So it's really a measure of distance. It's the average distance that the data lie away from the mean. So the variance and the standard deviation is the average distance that data lie away from the mean. The variance just squares that. So when we're thinking about the variance, we're thinking about how far away from an average, an informative average, is my data. So between group variance, within group variance. Another way of thinking about it is group means versus overall mean. Divided by individual data versus group mean. And as we often do, we're going to reject the null hypothesis for large values of F. So if your group means are far away from the overall means, but your data within each group are quite clustered. So this scenario the distance, right? Remember, we're thinking the distance, the variance. The distance of the data to the group means is small. Distance of the data to the group means is small. And the distance of the group means to the overall mean is large. And notice that it's all relative, right? So these are these guys. These are these guys. We're going to end up rejecting the null. Most likely will reject the null. Because the average distance of the purple here, there, and here is bigger than the average distance of the blue, right? Between group variance is the purple, within group variance is the blue, visually. How would I change that picture to now fail to reject the null? Well, to keep my averages the same, if I want to keep my averages the same, I need to increase this denominator. So I need to increase the distance that individual data points lie away from the group means. So now, to fail to reject, I need to increase this, and well, it will be a little bit silly because I made my means pretty far apart, but I will now maybe introduce a few outliers. And so now my individual data versus the group mean is something like this. Average distance of the data to my mean. And so this ratio is now far more closer to 1. You end up rejecting for something like 3 or 4 over here, but it depends on your degrees of freedom. So for now, I have shown a visual. So when you're plotting your data, remember every good analysis begins with a plot of the data. You're thinking, okay, how do my averages, group averages, compare to the overall mean? That's the numerator. And how does my individual data compare to my group means? That goes in the denominator. The bigger this ratio, the more likely you are to reject the null. Let's put a formula up on the board, but I don't want you to worry about the formula too much because we're not going to be doing this by hand. We're going to let software figure it out for us. It's just not worth it to do this by hand. I don't think we end up learning this. But we're going to start to get at these degrees of freedom a little bit. So not only is it a ratio, it is technically a ratio of ratios. That's why the formula is kind of not always worth keeping track of. All right, so we're going to use 2 indices. We're going to use the I index for observation, and we're going to use the J index for group. Spelled observation right, spelled group wrong. The I index for observation, the J index for group. The numerator is the sum across all the groups. G is my total number of groups of sample size per group and then we have, you know what I'm going to do? I'm going to color code it. Y bar J, that's the group mean. minus the overall mean. Squared because it's the variance, or something that resembles the variance, right? So the numerator, sum across all the groups, sample size per group, the distance between the group mean and the overall mean. And I said it's the ratio of ratios. So we divide by the number of groups minus 1. And the number of groups minus 1 is our degrees of freedom. So sometimes it's called degrees of freedom 1. Sometimes it's called degrees of freedom of the numerator, because this entire thing is in the numerator of the test statistic. The entire thing is in the numerator of the test statistic. All right, so the bottom is going to be something divided by the degrees of freedom. So I'll make a little placeholder here. And this next thing is going to be degrees of freedom 2. Sometimes this is called degrees of freedom 2. Sometimes this is called degrees of freedom denominator, because the entire thing is in the denominator of the test statistic. And in the end, these 2 degrees of freedom come into our sampling distribution, and where we find p-values, critical values, etc. So now the only thing left is this, the variance of individual data versus the group means. And so we're going to have a double summation. I told you it's not worth working out by hand. So we go J, remember J indexes group, I indexes observation. Sum over groups, sum over observations. What are we summing? Well, we're summing the squares. Summing the squares of, all right, here is my individual data. Minus versus the group means. And, right, this is the group mean as well. Degrees of freedom is going to be, I'm trying to color code the best that I can, N minus G. So the first degrees of freedom is number of groups minus 1. And the second degrees of freedom is N total, number of people, number of observations, minus N groups. Okay. So let's talk about some assumptions. I want to put these up because although I don't think this is the most useful statistical test, it is still helpful for us to know some of the assumptions. So there are 3 assumptions. First is that the populations are normal. The second one, the population group standard deviations are identical. Number 3 is that the data are independent. These are the assumptions. So this third assumption of independence, the data are independent, we also make this for the t-test. And well, it can be hard to test. You know what? All 3 of these can be kind of hard to test. But we also make it for the t-test, and we have to think, well, if the data were actually recorded over time, then probably they're not independent, because observations that were near each other in time are going to be more similar than the ones that are far apart. Similarly, if we're collecting data in space, then the observations that were nearer to each other in space are probably more similar than the observations that are far apart. It's actually called the first, Tolber's first law of geography. Can be difficult to verify. Populations are normal. So that is for each one of your groups. And oftentimes, you know, how big is the sample going to be within each group? 10, 15, 20, 30? It can be difficult to determine that each one of your population distributions is normal. Population group standard deviations are identical. I think that's the one that is the hardest one to verify. But people tend to say, you know, look for twofold, you know, anything that is greater than a twofold difference. If anything, if you get standard deviations that are greater than a twofold differences, this assumption is probably violated. Populations are normal. Geez, that can be hard with smaller sample sizes. The recommendation is try for maximum robustness. Keep these guys, sample sizes per group, the same, and as large as possible. For maximum robustness, keep the sample sizes per group the same and as large as possible. And that will give you the greatest chance of meeting all three of these assumptions that are, frankly, a little difficult to verify. Okay? So here's the other thing. So we find a test statistic. And we'll go through an example in class where, you know, you will run an ANOVA using SAS, and it will give you a test statistic and a p-value and the degrees of freedom. And now you know where these things come from. Suppose, you know, okay, so maybe you had 3 hospitals, 20 patients per hospital. So that means that our degrees of freedom 1 is 3 minus 1, right? 3 hospitals, 3 groups, and we're comparing wait time in the emergency room. Okay, so we're comparing 3 groups, 3 hospitals. Our first degrees of freedom is 3 minus 1, which is 2. Our second degrees of freedom, 20 patients per hospital, means my overall N is 60. My degrees of freedom 2 is 60 minus 3, number of groups, 57. And oftentimes this is reported like this. You know, my F statistic 257 is 9.98. P-value 0.0002. If your test statistic is 9.98, these 2 degrees of freedom, you have a lot of evidence against the null. What's the null? Well, the null is that my mu1 is equal to mu2 is equal to mu3. My alternative is that at least 1 mu is different. With this p-value, we reject the null. So we're saying that, well, it is not the case that the 3 population means of our hospitals are identical. But this is where I feel is one of the biggest limitations of the ANOVA is we rarely can just stop here. We rarely can just say, okay, so the 3 hospitals differ according to their wait times, because it takes exactly a millisecond to then ask, okay, and which one is worst? And the ANOVA can't answer that. The ANOVA can only tell you there's at least one meaningful differences there. But how many, see, we reject. And when we reject, we almost always have to then say, okay, so I rejected the null. We need to perform pairwise mean comparison. So for my example, you'll be asking, well, which hospital is better and which hospital is worse? So with 3 means, right? You can make mu1 versus mu2, mu1 versus mu3, and mu2 versus mu3. Each one is sort of like a t-test. So you very much can use a t-test, but you shouldn't. When you are comparing, when we compare more than 2 population means, at some alpha level, our false discovery rate, we need to adjust either the alpha or the p-values / confidence intervals. Why do we need to make this adjustment? Because if I am performing a lot of these comparisons, I'm going to falsely reject alpha % of them, right? What this means is we'll make alpha times 100% false discoveries across all pairwise comparisons. That's a bad thing. That's why we need to make the adjustment. Need to adjust. So these adjustments, the adjustments for multiple comparisons, fall outside the scope of the class. But I will just put 2 out there because they're by far the most common. There is a whole branch of statistics that deals with this, actually. Adjustments for multiple comparisons. Sometimes this is called adjustment for multiplicity. The most conservative is called the Bonferroni. Sounds like pasta. Sounds delicious. I'm hungry. So the first one, it's the most conservative, means that we're going to end up deciding, after rejecting this null, that the fewest of these pairwise comparisons are actually significant. So you only perform the multiple comparison adjustment after rejecting this null. And what do you do with the Bonferroni? This one is easy to remember, and that's why I think people use it a lot, but it's the most conservative. Instead of alpha, we use alpha over the number of tests. So my example has 3 tests. So instead of 0.05, I'm going to use 0.05 divided by 3. That's a 3. But you can see how this can get out of hand. What if you had, instead of 3 hospitals, what if you had every hospital in the state? What if you had 50 hospitals? All right, 0.05 over 50. What if you had, instead of 50 hospitals, you had something that you were measuring across every single gene? You probably have 1 million genes. So your alpha becomes 0.05 over 1 million. That is why it's considered the most conservative. It is really hard to reject each individual comparison using this new alpha. And again, we only worry about it after this omnibus null hypothesis, this global null is rejected. So Bonferroni adjusts the alpha by dividing it by the total number of tests. The other one is called the Tukey, and it's HSD. I always thought it was interesting. HSD stands for honestly significant differences. Honestly significant differences. It adjusts the confidence intervals. And p-values. It is a middle of the road option. So I think that's another reason why, if you don't want to use the Bonferroni, which is probably the easiest to apply, you use the Tukey HSD. And by the way, in SAS, and we'll see in class, these are simple options to just bring up. So you run your ANOVA, you either will reject or fail to reject the null. If you fail to reject, you know what, that's a big finding. You have no significant difference between any of your group means. If you reject, then you know at least one of your group means is different. And now we have to go looking. So what do? Well, we have to then perform pairwise mean comparisons. With my simple example, I only had 3, but you can see how that can easily increase. We have to make an adjustment to keep the false discovery rate in check. And I'm hand waving here because this is outside the scope of this class, but the 2 most popular ones, at least for general biostat, is Bonferroni, most conservative. Instead of alpha, we use alpha over the number of tests, or Tukey HSD. It adjusts the confidence intervals and the p-values to ensure that your overall false discovery rate remains at alpha. All right, so that takes care of the ANOVA. As I said, we will see an example in class. Don't worry about filling this out by hand. And I will see you in the next video when we talk about chi-square tests. See you later, guys.